Good afternoon, students. Today we shall talk about the partition function. It is a very important portion of statistical mechanics. Especially, it is very important for reading or understanding the statistical thermodynamics portion. Before going to the partition function, I shall just little bit try to remember that what we learned from the quantum mechanics, that if we deal with the distinct quantized energy state. So you can see in the picture that I have shown you that the three energy state E1, E2 and E3. So these are level 1, level 2 and level 3 of the energy, and each of the energy level consists of several states actually. That in case of the first level, it has two state 1 and 2. Basically the degeneracy G1 equal to 2. The second level which is only one degeneracy, so it is the degeneracy is 1, and the third level has the three energy states, that is the G3 equal to 3. So what we know that from the knowledge of our chemical equilibrium, that more states means more likely, means from this picture it is very much obvious to us that it has the more number of states, that is the G1, 2 and 3, that is this level 3 has more number of states, so the more occupancy should be there. But before going to that, what we have learned the last day actually from Boltzmann distribution, that I am coming. That according to Boltzmann distribution law, the fraction of molecule, that is Ni, in a particular state I at temperature T with energy Ei is given by Ni by N equal to Gi into e to the power exponential minus Ei by kBt, which is a Boltzmann constant, and sum over Gi into e to the power minus Ei by kBt. So if you read the note that I have sent you last day, you can find this formula is there. While we have proved this formula only, that Ni by N equal to Gi into e to the power Ei by kBt, sum over Gi by Ei by kBt. So Boltzmann distribution gives you the occupancy or the fractional occupancy of molecules in each of the energy state actually. So now if I come to the earlier picture, then if I found it, what I am doing, that I have told that more states means more likely to occupy actually. So I am drawing the level of the energy state. So you can find that energy is increasing as I am moving from the lower portion to the upper portion. So it means the E3 has the higher energy compared to the level 1, that is E1. So according to the Boltzmann distribution or the probability theory of observing these states, we can write that Pi is proportional to Gi into exponential Ei by kBt. So what does this imply? That the fractional partition that I have learned or we have learned from the Boltzmann distribution, it can be summarized in this way, that this partition function is, this fractional occupancy is proportional to both the number of states in each energy level as well as the corresponding energy, right? You see that there is a decrease as you are moving to the higher energy level, there is a decrease in the thing. So the balancing between these two opposite thing in our picture gives us the proper picture that how much fractional occupancy will be there. So if I want to try to avoid this proportionality sign, so what we can do, we can put equal sign, and what after deleting the equal sign, so we can put a constant, that is C. So which in this case we can take it as a proportionality factor. So C is the proportionality factor. So it means that Pi equal to C into Gi exponential minus Ei by KBT. Now what we learned from the probability theory, that if you added all the events or all the fractions of the molecule, all the fractional occupation of the molecule, because our total number of molecules is same and our system is closed system, so then sum over I equal to 1 to n, that where n is the total number of molecules, so Pi equal to 1. So all the probability, addition of all the probability should be 1, which is another way we can tell it is a process of normalization, which we do maximum of the cases. Now just to see that Q equal to Q equal to sum over I equal to 1 to states. If I take only states, means level 1 2 3, then e to the power minus Ei by KBT, that's equal to sum over I. If I goes to the level, which level correspond to the degeneracy also, because each states constant somewhere in case 2, in case second case 1, and third case 3 levels. So Gi into e to the power minus Ei by KBT. So this thing is being called as a partition function. And what is the main importance, because what we have learned about wave function in quantum mechanics, this is almost similar way, that all the information about the system is laid in this partition function, right? So learning partition function is very important part of understanding the statistical thermodynamics. So if I remember the earlier equation, that Pi equal to C into Gi e to the power minus Ei by KBT. So if I replace this C by 1 by sum over Gi into, so the total equation looks like this, that Pi equal to Gi into Ei by KBT, sum over I equal to n Gi e to the power minus beta Ei. So sometime I can write it as a 1 by Q into Gi into e to the power minus Ei by KBT. So where Q is called the partition function. So we can understand that if you remember the molecular fraction definition, then we know that all the molecules basically which is being dissolved in a solution, it is in the denominator, and the particular molecule or the which one we are interested, that is on the numerator. It is also same case that the energy level we are interested, that is in the numerator, and it basically corresponds to the adding all the molecules and their corresponding energy state. So it is very important function, that is Q is a partition function. Now you can ask me a question that, sir, in a short, what we can understand from the this partition function. So partition function is a measure of the volume occupied by the system in phase space. I have already introduced you what is phase space. So phase space is nothing but it is a space which is surrounded by different coordinates, and each of the point basically denotes each of the system. What we have learned in earlier classes, that phase space is a two-dimensional expression of each of the particles' position as well as its momentum. So these are the two coordinates there, that momenta and position. And basically what the partition function tells, actually basically it tells you how many microstates are accessible to your system in a given ensemble. So if you are dealing with some ensemble or some system, depending on the nature of your ensemble, it can be canonical, microcanonical, grand canonical, but whichever the ensemble it may be, depending on its other conditions, what we get from the partition function, we get that how many microstates are accessible. It means that if you want to measure the energy, right, so if you try to rearrange the molecules, you have been given 10 or 15 molecules, and you have been given and 15 or 20 energy states. Now you have been told that you have to arrange these molecules. So what this partition function will do, if you know from earlier that what is the partition function, that first thing you will know the total amount of energy. Total amount of energy you will know. And second thing what you know, that with that much total amount of energy, depending on other conditions also, that the properties means temperature and other properties that has been given to you, you can access how many energy levels to arrange or rearrange those molecules or atoms, whichever is given to you. So accessible, maximum number of accessible energy states is being told by this partition function. So kindly again I am rereading that the partition function is the measure of the volume occupied by the system in phase space. So there are two types of partition function. One is called the system partition function, another is called the molecular partition function. What is system partition function? Partition function for an assembly of n identical molecules is called the system partition function. Partition function for an assembly of n identical molecules is being called as system partition function, and it can be calculated from each individual partition function of the each molecule of the system. So it means that if you have three particles or three molecules, you add all their individual energy, and when you add up you will get the three values, and add those three values you will get the total partition function of the particular system. If your system consists of three molecules or three atoms or any other, whichever the particles you are dealing with. So this system partition function can also be of two types depending on the type of the particles we are dealing with. One is the distinguishable partition function. Distinguishable case is basically we are mentioning here about the crystal. So in case of crystal, then this Q equal to small q over n. Here is n is the total number of crystals, or total number of molecules which are we dealing with. So it is the individual partitions. Small q is the individual partition function, and this capital Q is the total partition function. And another one is the indistinguishable. Indistinguishable means that if you are dealing with some gas, so in this case it is generally what happens, that since it is indistinguishable, so automatically depending on our permutation theory, what we have to do, you have to just deal with that, you have to divide it by the n factorial just to avoid the recounting. So hope all of you have understood up to this much, that system partition function. So what is the another partition function? Another partition function is called the molecular partition function. So molecular partition function, it depends on the number of modes accessible to a molecules, because we know that while we have learned the spectroscopy, we have learned about the vibrational spectroscopy, rotational spectroscopy, electronic spectroscopy, like this. So there are also several modes are like that. Generally, principally there are four type of modes: transitional motion, vibrational motion, and rotational motion, and the last but not the least, that is the electronic motion. So since the partition function basically describes that where the molecule is moving from one energy state to another energy state, and modes are the different, that it may be transitional, it may be vibrational, it may be rotational, or it may be electronic. So we can divide this molecular partition function in other four another classes, that is transitional partition function, rotational partition function, vibrational partition function, electronic partition function. Broadly classify in these four different modes where the molecule can move from one energy state to another energy state. Because our main target is to justify or understand that the actual energy or the equilibrium energy of a system, because statistical mechanics deals with the quantum mechanics in one side, and another side it is the macroscopic system, and it is a linker between these two. So we are dealing with the molecule, but we are trying to predict that what it will do it will do when we have a very large number of molecules. So we are trying to get the behavior of a large gathering of molecules from a condition or situation of a single molecule. So this is the statistical mechanics actually. So this molecular partition function basically take care of the different type of modes of molecule that is accessible to a molecule while it is in motion actually, because we know that molecule is in motion all time. So now we shall have some elaborate discussion regarding the translational partition function. Translational partition function is denoted by QTR. QTR. So system partition function, there is a capital Q, and in this case it is small q TR, because we are dealing with the particle. So transitional partition function basically it deals the movement of center of mass of a molecule. Movement of center of mass of a single molecule. So how it translate? It may translate along x-axis, may along y-axis, or may along z-axis. So what we have learned in the simplest thing we have learned in quantum mechanics, that is one-dimensional box. Since one-dimensional box is an absurd imagination, so better what the thing we have developed, which is basically almost real thing, that is a 3D box. We shall deal with a 3D box whose we are dealing with a particle whose mass is m, and this particle this box have the length, breadth and width is a, b and c. So x, y, z, I am putting here a, b, c.